Hi folks, welcome to this video on biomechanics, the topic focusing on scalars and vectors. Okay, we're going to do quite a lot in this one, but hopefully it'll all make sense. And like I said, keep referring to these videos. You can pause them, you can rewind them, you can go over certain bits to make sure you're absolutely happy with everything. First and foremost, scalars and vectors. Sometimes we're asked to just give a definition of each in the exam, so let's start with that. Okay, so scalars are things, measurements based on size or magnitude only. Now, what we mean by that is, for example, if you see a car going past at 30 miles an hour, that is a scalar because you've just given its size or its magnitude 30 miles an hour. Equally, if you weigh 86 kilograms, that is a scalar as well because you are just giving an indication of the size of something. Okay, so where do vectors differ to that? So vectors have size and direction. So if I was to say to you that car is travelling at 30 miles an hour in a westerly direction, I have changed that scalar into a vector. Okay, now what is the significance of the two? In sport, in biomechanics, we are obsessed with vectors. Okay, it's no point knowing how much force an athlete has generated, how much force they've pushed into the track or their starting blocks or something like that, unless we've also got an indication of the direction that they've applied that force, because the direction you apply force dictates which direction you will then travel in. Take a shot putter, for example. What's going to win her the gold medal in her event is the amount of force that she puts through that shot as she pushes as hard as she can. But equally, the direction and the angle in which she pushes it. She can push it with all the force that she likes, but if she pushes it out too flat, it's going to come down sooner. If she pushes it too high, it's going to come down not very far away from her body. She's got to get the angle right. So we are obsessed in the sports world to do with vectors, in terms of biomechanics. And the two vector quantities that we are most obsessed with in sport are velocity and acceleration. Okay? How quickly are you doing something, shifting your body weight, shifting someone else's body weight, shifting that object? They're the two vectors that we are both obsessed with. Why are these vectors? Well, hopefully we shall show you why. That is how you calculate velocity. People often confuse, or not confused, but say velocity is speed. It is speed in some way, shape or form. Speed is technically distance divided by time. Okay? Velocity is more technically displacement divided by time. Displacement is similar to distance, but it's when you have displaced something, it's the distance away from your starting position. So the displacement of a 100-meter runner is 100 meters from their start line. And I know that's very similar to distance, but displacement also takes into consideration direction. Hence why velocity is a vector quantity, because this is distance with direction divided by time. And if I've got a size and a direction, so that I've got a distance of a certain number of meters and a direction that I have travelled in, that makes this thing, displacement, a vector. And because I'm dividing a vector by time, it makes velocity a vector. So velocity is a vector quantity and it is displacement divided by time. Now, something I should add just before I go to acceleration is, because displacement is measured in meters and time is measured in seconds, velocity is measured in meters per second. Okay? Where does acceleration differ to this? Acceleration is the change in velocity in meters per second divided by time in seconds. So the acceleration is measured in meters per second or meters per second squared, whichever you prefer to use it. So remember, acceleration, change in velocity, I could be getting quicker or I could be getting slower. So acceleration and deceleration can both be calculated from this. And again, because we're taking velocity into consideration, and velocity is a vector, because displacement is a vector, acceleration is also a vector. I will accelerate in a certain direction. 100-meter runner will burst out the blocks and accelerate in a given direction in order to win their event. Okay, they will also decelerate in a given direction in order to stay in their lane. So velocity and acceleration are both vector quantities, and that is how we calculate them. Now we're going to return to velocity and acceleration right at the end, but first of all, we're going to just look at something else that can come up on the exam with regard to scalars and vectors and velocity and acceleration. This is quite difficult, so we're going to take it back a notch and build it up to the really difficult stuff. But again, these next few slides do contain things that could come up on your exam. Right, these things are called pin diagrams, okay? Sometimes they won't call them that. We've had a recent question on this on the exam, not to, it didn't mention pin diagrams, but it wanted exactly this. Right, there are 4 forces that can act on a person when they are moving at any one moment in time, okay? Okay, and that is them there. So we've got, let's get a marker on here, we've got gravity, we've got a ground reaction force, we've got friction, and we've got air resistance. These forces are acting on us all day, every day. As you would expect, gravity is always acting down. It's always trying to pull us back down to planet Earth, and it's always succeeding in doing that. Okay? Ground reaction force is what we do to counteract gravity. It's contracting muscles in your legs so that you can stay standing upright. Okay? Friction, on the other hand, it drives us in a given direction. Okay, so if I just get a pen there, for example, it could drive us in that direction, or it could drive us in another direction. And finally, air resistance acts against our direction of travel. Air is pushing back on us, right? So let's have a look at this picture of Usain. I'm just going to move it down a second, just so I've got a bit more space. Right, what can we say about Usain Bolt on this picture here? Right, number one, we can say that gravity is acting down, hence why he is staying on planet Earth. Okay? However, he's not falling into the ground. He's not going, face down into the track, which means his legs in contact with the ground must be doing a ground reaction force. And if you look very closely, I've done arrows of the same size. What I've just done then is I've drawn a vector. Look, the arrow is given a direction and the length of the arrow is given a size. So it's got size. Each of these forces here has size and direction. So gravity is pulling me down with that value, but the ground reaction force is equal in length but opposite in direction. So I stay on the track. In this instance, he doesn't take off into the air and he doesn't fall into the ground. Okay? Now, what is he doing to allow himself to drive out the block? He's producing a friction force in that direction there to drive himself forwards out of the block. Okay? And as he's doing that, air resistance is pushing back through the middle of his body there. But as you'll notice, again, there's the directions of air resistance and friction going that way, air resistance going that way. But if you notice, the friction one is longer, greater than the air resistance one. So he, in this instance, he's driving himself forwards, he is accelerating. Now why is the air resistance one smaller? Look at his position, he's crouched, he's low down, he's doing what all great sprinters should do at the start, stay very low to the ground. In a low position, that's going to reduce your air resistance. So what is the overall effect of this here? He is accelerating. He's accelerating out of the blocks. Just to quickly recap that, what I've done is I've drawn 4 vectors on here. I've drawn the 4 forces and the direction that they are travelling in, and the length of the arrow indicates the size of that force. That blue arrow, I could have drawn it all the way along here. As long as the blue one is noticeably longer than the yellow one, that indicates the fact that he is accelerating. Okay? Right. Stay with it. Let's move on to the next one. Right, so here we've got Usain in full flight. He's in full flight mode. Now, what is still happening? Gravity is still acting down. I'll just put there white equals gravity to remind you. Okay? His ground reaction force, the force produced by his legs in contact with the ground, is still acting up. And I'll just put GRF, ground reaction force. And again, look, they are the same length as each other, which indicates that they cancel each other out. hence why he's not jumping into the air and he's not falling flat on his face, but they are opposite in direction, showing that they are cancelling each other out. Now this time he's probably at midpoint in the race. This is where a sprinter's velocity will be around about the same. Between about 30 and 80 metres, he will be at top velocity, highest velocity, and he'll just look to maintain that. So in this instance, there is the friction arrow, showing that he is producing friction between his foot and the track, driving himself forwards. But also, because he's now upright, there's the air resistance arrow. Now if you look this time, if my drawing's any good, you'll see that these two are round about the same length as each other. So now these two are equal and opposite to each other, so they cancel each other out, and that shows now that he's running at constant velocity. He's neither accelerating nor decelerating, because that force, this force is equal and opposite to that force, and that force is equal and opposite to that force. Something else I've got to tell you to make sure that you're aware of it. If you look, I am drawing these arrows and I'm giving them what we call a point of application. What I mean by that is gravity always acts right down the middle of his body. Don't draw a gravity arrow outside of the human body. You won't get marks for it. Air resistance acts through the middle of his body. A ground reaction force is generated by the contact leg in contact with the ground, and also the friction force is where the foot is in contact with the ground. So you've got to make sure you're drawing the arrows in the right direction, you're drawing them to the right size, and you're giving them what's called point of application. They're acting through the athlete's body in the right position. Right, there's one more stage of this 100 metre race to look at. Now here is that classic 100 metre final where he literally eased off with 20 metres to go and still absolutely destroyed everybody. Now, what can we do again? Surprise, surprise, gravity is acting down. Always has done, always will do, unless something goes really badly wrong. Okay, his ground reaction force, his GRF, is acting up where his foot is in contact with the track. But if you notice this time, because he is eased right down, because he's taken his foot off the gas, his friction arrow is not going to be that long at all. But because he's eased right off and he's opened his body up nice and wide, his air resistance arrow is going to be greater in length than his friction arrow. So what's he going to do? Now he's going to decelerate. He's going to slow down. Okay? What you've just done there, what you've seen me do and what you need to be able to do is do that. What you've just drawn is a series of vectors. You've drawn arrows that have size, indicated by the length of the arrow, and direction, indicating which force, the direction that force is acting in. And you can do that. If the forces are equal and opposite to each other, they cancel each other out. And the athlete will remain in a constant position. It might be that they remain still or they move at constant velocity. Okay? That's always been the case for a sprinter with their gravity and their ground reaction force arrows. They're always equal and opposite to each other, so they cancel each other out. The two that vary on a sprinter are the friction and the air resistance. So friction will be greater at the start than air resistance, so you will accelerate. Midpoint in the race, friction and air resistance will be equal and opposite to each other, so you'll move at constant velocity. And towards the end of a race, air resistance will be greater than friction. It might be that air resistance hasn't increased. You know, the air resistance is that you've not suddenly got a gust of wind. But the fact is, as they get towards the back end of the race, the muscles are getting tired, so friction is reducing and it drops below the air resistance figure. And that's why you start to decelerate. So that is how we draw pin diagrams for athletes. How else could we do it? Just really quickly, this is the kind of question that came up a few years ago. If you look at these two athletes here, you've got Blanka Vlasic and Dwight Phillips, right? You've got a high jumper and a long jumper. Now, go back to your AS movement analysis. Both of these are going to extend their knee at takeoff by contracting the quadricep. They're going to extend their hips at takeoff by contracting the gluteals, and they are going to plan to flex their ankles by contracting the gastrocnemiae. But how come one of them is going straight up and the other one is going along high, lengthways, trying to do a jump as far as they can in a horizontal direction? It's all down to vectors. The same muscle groups can contract, but you can produce a different vector. So for example here, if we look at Blanka Vlasic during this takeoff, she has got gravity acting down, okay, but because she's doing a very, very big powerful contraction for this very brief moment in time, her ground reaction force is going to be greater than gravity, so the arrow is longer, so she's going to escape gravity for a very brief moment in time and fly over that bar there, okay? But what you've just done is you've drawn a vector, okay? You've taken a look at these two forces, whereas someone like Dwight Phillips, okay, he's going to put more into the horizontal. And what I'm basically trying to show here is you can sometimes draw it like this. That is the classic high jump vector, and that is the classic long jump vector, okay? That's horizontal force, that's a vertical force, there's a horizontal force, there's a vertical force, sorry. So what's basically going to happen here is Blanka Vlasic is going to put a small amount of horizontal. So when she contracts her takeoff muscles, a small amount of that force is going to be applied in a horizontal direction, but the bulk of it is going to be applied in a vertical direction, and she's going to do that type of movement. She's going to go in that direction, which is exactly what she wants in a high jump. Similarly, Dwight Phillips is going to contract those exact same muscles as Blanka Vlasic is, but he's going to apply more of that force into a horizontal direction and less into a vertical, and he's going to have a vector that looks something like that, and that's what's going to allow him to win his event. So vectors are forces being applied in certain directions that allow you to move in the direction you want to move in, okay? What you've got to be able to do is draw that diagram and say that you've got, but the thing that you've got to do with the arrows is show where that force has been applied, okay? Like you did with Usain Bolt, where is that force acting through the athlete, okay? Now, coming full circle, coming back to what we did at the start, we looked at velocity and acceleration. What you've got here is Usain Bolt's actual velocity time graph from the World Championships he won in 2009, where he did that staggering world record. Okay? Now, what you've got here is the distance. There's 0, there's 100 metres. Okay? What you've got is his speed. This should technically, you know, because it should technically say velocity, but what you've got there is it's showing you where he is fast and where he is slow. As you can see, these are his velocity readings. So 6.85, that means at this point here he was doing 6.85 metres per second. At this point here he was doing 11.05 metres per second, 11.54 metres per second, 11.82 metres per second, 11.4 metres per second. That fits in with the pin diagrams that we've just done, and hopefully we shall see why now. What is this area of the graph showing here? It is showing rapid acceleration. And that's indicated by the steepness of it. It's a very steep line showing that he's getting up to very, very quick speeds in a very short distance. He has gone from 0 metres per second to 11.05 metres per second by 30 metres. 30 metres into the race. That is rapid acceleration. So if you think back to that first pin diagram, when he was exploding out the blocks, the friction force is very high, the air resistance is very low, ground reaction and gravity cancel each other out, so he's going to accelerate very, very quickly. What you see here is gradual, and I've got to be honest, slight acceleration. But largely what we are seeing is, look at that, 11.54, 11.82. We're talking about not very much here. What we're actually seeing is relatively constant velocity. Yeah, I know the graph is going up ever so slightly, but you know, compared to what it was doing at the start there, that is very, very slight increase in acceleration. That is relative constant velocity. So that's that second picture we looked at, where Usain, all forces were equal to each other and acting in opposite directions, and he was running at the set speed. Okay? Finally, what we are seeing here, if you notice, is slight deceleration. Okay? He is slowing down. This is where the friction has dropped. The air resistance is now slightly higher than friction, and he's going to be slowing down as he approaches the line. You know, maybe because he's eased off, maybe because he's got tired, but we often see that with the vast majority of sprinters. That's what it looks like. So this is a velocity time graph showing how velocity changes over the course of a 100-metre race for a sprinter, and how it fits in with those four forces that we spoke about: gravity, ground reaction, air resistance and friction. Just one quick little thing. The other reason that some of you might be thinking, and if you have, brilliant. Why else do they slow down here? Well, link it back to anatomy and physiology, link it back to your energy systems. At around about this 80-metre mark, they're going to be running dangerously low on PC, phosphocreatine. So that's another reason why the friction is going to drop. The air resistance is going to stay fixed throughout that 100 metres. Like I said, barring a massive headwind suddenly out of nowhere, the air resistance is going to be relatively fixed for 10 seconds. But the friction is going to drop because you're running out of PC. You can't put the force into the track. You can't drive forwards. Finally then, the only other question that they could really ask you on scalars and vectors are vectors acting on a throw. Okay, so let's say you've thrown something. It could be an American football, it could be a cricket ball, rounders ball, netball, something like that. You're going to see a general flight path that looks something like that. And we'll deal with flight paths when we look at projectiles, because that's what a projectile is, something that's flying through the air. It could even be, you know, a long jumper, their own body is a projectile as they take off, for example. But let's say you've thrown something and it follows that flight path, okay? At every stage along this flight path, okay, whoops, just quickly get rid of that little dot there. At every stage, it is going to have a horizontal force acting on it. And the reason I'm talking really slowly is because I'm trying to do this right. What I should have been able to do, although I probably haven't, is that those horizontal arrows should be about the same length as each other. Near as damn it. Why? Well, again, it's a vector because I'm giving it direction and the length of the arrow is giving you an indication of size. Why should the horizontal arrows not change at all? Because it's always travelling forwards. Okay? So if it's all, you know, it's not doing that and then just plummeting out the sky, it's always travelling forwards, which means that the horizontal forces acting on it should always be constant. Okay? So point number one, if you're ever asked to draw vectors on an object that is flying through the sky, the horizontal ones are going to be equal at all points through that flight of that object, okay? As I've tried to do there. Here's the one that's going to be different though. The vertical forces are going to be slightly different. When I initially throw it or kick it or whatever, the vertical forces are going to be acting in that direction. Okay, because it's travelling upwards. However, by the time it gets to the top of the flight, there are going to be no vertical forces acting on that object because there's a very brief moment that it just flies perfectly horizontal. So we're only going to have a horizontal vector at the top of a flight. After that, the object starts coming down to earth. And why? Because gravity has taken over and is now pulling this object back down to earth. So vertical forces, vertical vectors do change on the flight of an object. Just look at it this way. Think about our long jumper and high jumper vector thing. Do you remember when I drew those things that looked a bit like that? Okay. Look what, and we said that's where the high jumper is going to go. That's where the long jumper is going to go. Same as this, look. If I give it a vertical and a horizontal, it'll fly somewhere between the two. If I give it a vertical and a horizontal, it'll fly somewhere between the two. If it's just got horizontal, it'll just fly flat. Then if it's still got the horizontal but gravity's taken over, it'll fly downwards on that direction. Again, still flying horizontally, but downwards, and it'll continue down into the ground. So with vectors, you're always trying to draw us to show the direction and the size of the force. That is a lot to take on board. So have a look at this video as many times as you want, read the booklets, and also have a go at the tasks in the booklets to help you understand this.